In this video, I'm going to go over alpha decay, which is one of the possible radioactive decay types for a radioisotope or any isotope of an element that will radioactively decay because it has an unstable nuclei. I will also go over beta decay, gamma emission, and the other types of positron bombardment and spontaneous fission that are on this set of notes. And I'll also try to go over band of stability and how you know if a isotope is going to be a radioisotope and decay because it's unstable. But in this video, I'm going to focus just on alpha decay. So if you want access to this set of notes, you go to the YouTube description below. You can print this back, double-sided or back-to-back. It'll be one sheet of paper. When you fold it in half, this will be on the inside of alpha decay. But what I'm going to do right now, just to help us make sure we know that this is alpha decay, which is one type of radioactive decay if you have an isotope that is unstable. And this is what I'm going to go over in this video. So we're going to go through a few things that are going to go on the inside of here. Kind of some facts about it. We're going to try to draw sort of some nuclei pictures or particle pictures, and then we're going to go through these practice problems that I have here on the side. All right, so let's get started. So the first thing I'm going to do is just bullet off some things about alpha decay or alpha particles. Alpha particles can travel about 2 to 4 centimeters in air. So they really can't travel very far in air. And then the tissue depth, if they were to collide with you, is only about 0.05 millimeters of tissue depth. And then last but not least, how do you stop an alpha particle from kind of colliding kind of with you? Is it stopped by or shielded by just paper or clothing? And then the most common example of radioactive decay, that is alpha decay, is the radioisotope of radium that is 226 for a mass number and 88 for an atomic number. So what it's going to do is it's going to emit an alpha particle, which we have to learn what that is. And then hopefully it's going to emit a more, and I'm going to put more, stable nuclei. Because there's a possibility that that more stable nuclei still isn't completely stable. So what I'm going to do is draw kind of like a particle picture of the protons and neutrons. Now, because this is such a large radioisotope or isotope, I'm not going to be able to count the exact number. So I'm just going to kind of, just tell you how many there would be. And again, this is on the inside of this piece of paper if you print it front and back, or I guess on the back side. So what I'm going to do is kind of draw out what this would look like. So if I have radium 226 and 88, that means that there are going to be 88 protons. I'm just going to put a little list, 88 protons. And then if I take the 88 and I subtract it from the 226, that's the number of neutrons. So it's 138 neutrons. So because I don't want to spend a lot of time on this video drawing the exact number of protons and neutrons, because it would take a long time, I'm just going to kind of add some protons. These are my protons, okay? And really I should be adding, 88, okay? And then there should be 138 neutrons. But for the sake of this video and for us not to draw that many circles, we're just going to say that this is, approximately a radium, okay? Then what happens is this ejects two particles, okay? It ejects a alpha particle. So an alpha particle is actually easier to draw. It's 2 protons, 2 neutrons, okay? And so if you want to list that, it's 2 protons, 2 neutrons. And an alpha particle is a helium. So if you have a periodic table handy, helium has an atomic number of 2, and one of the most common isotopes, in this case for helium, is 4. But I'll be honest, this is actually a charged particle. It's actually a 2+ particle. And this is the alpha particle. All right, the next thing is then what's left. Like what's left if you take off 2 protons and 2 neutrons? So the first thing I'm going to do is say, well, then this goes to 86, because if I take off 2 neutrons and 2 protons, the top number is actually going to go down by 4. So I have something that's 86 for an atomic number and 222 because there's 2 protons and 2 neutrons that are now missing from the mass number. And then I'd go to a periodic table and I'd have to figure out, well, which element is 86, and it's radon, so Rn. And that's kind of how you approach these problems, is you have to figure out kind of what comes off of it. In this case, we're doing alpha particle in this video. And there's 86 protons. Actually, let me put that kind of on the top again here. 86 protons. And then there would only be 136 neutrons. So if you add this up, this is going to equal 222, whereas this would have equaled 226. So that's this problem right here in the middle here. And so what I would write is, if it was a nuclear reaction, I would just write then that this had a alpha particle that came off called a helium, and I would just place it into, so I'll just kind of box this out, place it into that reaction as a product, meaning that it produced a helium particle and then a radon isotope. All right, so let's just try these last 2 examples here and here before I kind of end this video and then move on to beta decay. So the next video will be about beta decay, and then I'll go over gamma decay and then the other types. So what we need to do is we need to figure out what goes in this missing box right here. So what you notice from this one is that the mass numbers add up to the same mass number on the other side. It's the law of conservation. And then the atomic numbers add up to the same thing on the other side. Again, the law of conservation. So what I'm going to do then is just do a quick little math problem here. Let me erase that. So if polonium releases an alpha particle, that means it's going to have an 82 for an atomic number, because if I take 82 and I add it to 2, that's 84. And then if I take 4 and I subtract it from 210, that's 206. Now you need a periodic table and you need to find out, well, what element is going to be left. That's 82. And if you look here, you have lead right here as 82 and the capital P, lowercase b, and you've filled in that part of that nuclear reaction. All right, one more, and then, like I said, I'll end this video and I'll move on to beta decay in a separate video. I might even put beta decay with gamma. We'll see. So the next thing is we have to figure out maybe what did we start with. So this is where we have, well, what did we start on the other side with as a reactant of this nuclear decay. So kind of remember the rules is that the 92 and the 2, they have to equal the other side. So that means the other side is 94. And then the mass numbers for the law of conservation also have to add up. So that's 240. So now you go to a periodic table and say, what is element 94? And you find it. And element 94 is plutonium, Pu, capital P, lowercase u. And you have filled out your radioactive decay problem for alpha decay. All right. So like I said, in another video, I will go over the beta decay and maybe even throw in gamma, because gamma is actually pretty easy. If not, it'll be 2 separate videos, and then I'll move on to the other types. All right, so I hope this video helped you understand how to write nuclear reactions for alpha decay and kind of what alpha decay is in terms of being a helium with the 2+ charge, and then the mass number of 4 and the atomic number of 2, and kind of how it can be stopped by paper and clothing, and how far it can travel in air. All right, hopefully you'll watch the next video on beta decay.